Have you ever looked up at the night sky and wondered where stars come from? These twinkling points of light have captivated humanity for millennia. Stars, as we have come to understand them, are not static objects but dynamic entities, born from swirling clouds of gas and dust. These cosmic nurseries, known as nebulae, are the birthplace of stars, where the seeds of stellar evolution are sown. Within these vast clouds, hydrogen and helium, along with trace amounts of other elements, begin their journey to becoming celestial objects that light up the cosmos. The process of star formation is a delicate dance between gravity, which pulls matter together, and outward pressure, which tries to push it apart. Nebulae, these vast clouds of interstellar gas and dust, play a crucial role in the birth of stars. Within these clouds, gravity acts as a sculptor, pulling matter inwards, creating regions of increasing density. As gravity draws more material towards the center of these dense regions, the temperature and pressure begin to rise. The once diffuse gas and dust particles collide more frequently, generating heat through friction. Over time, these regions become hotter and denser, glowing with an eerie, ethereal light. These glowing clouds of gas and dust, illuminated by the light of nearby stars or the energy released by the collapsing cloud itself, are often visible from Earth as nebulae. As the core of a collapsing cloud of gas and dust continues to contract under the relentless pull of gravity, it heats up even further. The temperature at the center can reach millions of degrees Celsius, hot enough to strip electrons from atoms, creating a sea of ionized gas known as plasma. This hot, dense core, still shrouded by the surrounding cloud of gas and dust, is known as a protostar. It is not yet a true star, as nuclear fusion, the process that powers stars, has not yet ignited in its core. The protostar continues to accrete material from its surroundings, growing in mass and temperature. As its core temperature and pressure increase, it approaches the threshold where nuclear fusion can begin. If a protostar accumulates enough mass, the temperature and pressure at its core will eventually reach a critical point. At this point, a process called nuclear fusion ignites, releasing an immense amount of energy. Hydrogen atoms, the most abundant element in the universe, are fused together to form helium, releasing a tremendous amount of energy in the process. This energy, in the form of light and heat, radiates outward from the star's core, creating an outward pressure that counteracts the inward pull of gravity. The star achieves a state of hydrostatic equilibrium, where the outward pressure from nuclear fusion balances the inward force of gravity. Once a star achieves this balance and settles onto the main sequence, it enters a long, stable period of its life. Our Sun, a yellow dwarf star, is currently in its main sequence stage, and it is expected to remain there for several billion more years. Nuclear fusion is the heart of a star, the engine that drives its luminosity and heat. This process, which occurs in the extreme temperatures and pressures found in stellar cores, is responsible for the existence of all elements heavier than hydrogen and helium in the universe. In the core of a star, hydrogen nuclei, which are simply protons, are moving at incredibly high speeds due to the intense heat. Normally, these positively charged particles would repel each other, but under the extreme conditions in a stellar core, they overcome their electrostatic repulsion and fuse together. This fusion process releases a tremendous amount of energy, which is what makes stars so bright. The fusion of hydrogen into helium is the primary energy source for main sequence stars. This process can continue for millions or billions of years, depending on the mass of the star. As a star ages and consumes the hydrogen fuel in its core, it begins to evolve off the main sequence. The core, now mostly helium, contracts and heats up, while the outer layers of the star expand and cool, causing the star to become a red giant. Red giants are much larger and cooler than their main sequence counterparts. Despite their cooler temperatures, red giants are much more luminous than main sequence stars because of their enormous surface area. During the red giant phase, stars can undergo a variety of complex processes, including the fusion of helium into heavier elements like carbon and oxygen. These heavier elements are then dredged up from the core to the surface, enriching the star's outer layers. The eventual fate of a red giant depends on its mass, with more massive stars experiencing more violent and spectacular ends. For stars much more massive than our Sun, the red giant phase is merely a prelude to a truly spectacular demise, a supernova. As a massive star exhausts its nuclear fuel, its core collapses under its own gravity. This collapse happens so rapidly and violently that it triggers a shockwave that rips through the star, blasting its outer layers into space. This explosion, known as a supernova, is one of the most energetic events in the universe. For a brief period, a supernova can outshine an entire galaxy. These explosions are responsible for creating many of the heavier elements in the universe, including elements essential for life, such as iron, calcium, and oxygen. The remnants of a supernova explosion can linger for thousands of years, forming stunning nebulae that are visible from Earth. The Crab Nebula, for example, is the remnant of a supernova that was observed by Chinese astronomers in 1054 AD. After a supernova, the core of the star is left behind, its fate determined by its mass. For stars like our Sun, the core will become a white dwarf, a small, dense object about the size of Earth. White dwarfs are incredibly hot, but they slowly cool down over billions of years, eventually fading away into stellar remnants known as black dwarfs. For more massive stars, the core collapses further, forming even more exotic objects. If the core is between 1.4 and 3 times the mass of the Sun, it will become a neutron star, an incredibly dense object composed almost entirely of neutrons. Neutron stars are only about 20 kilometers in diameter, but they are so dense that a teaspoonful of neutron star material would weigh billions of tons on Earth. If the core is more than 3 times the mass of the Sun, its gravity becomes so strong that nothing, not even light, can escape its grasp. It collapses into a singularity, a point of infinite density, forming a black hole. The life cycle of stars is a continuous process of birth, evolution, and death. Stars are born from the dust and gas of nebulae, live out their lives fusing lighter elements into heavier ones, and eventually die, often returning their enriched material back into the interstellar medium. This material can then go on to form new stars, planets, and even life itself. This cycle of stellar life and death is essential for the evolution of the universe as we know it. Stars are the cosmic furnaces where heavier elements are forged, enriching the universe with the building blocks of planets and life. The death of stars, while marking the end of one stellar life, paves the way for the birth of new generations of stars and planetary systems. In this sense, the life cycle of stars is not just a story of individual objects, but a grand cosmic narrative, a tale of creation, evolution, and the interconnectedness of everything in the universe. Stars are not just isolated objects scattered randomly throughout the universe. They are fundamental building blocks of larger cosmic structures. They are grouped together in vast collections called galaxies, held together by their mutual gravitational attraction. Our own galaxy, the Milky Way, contains hundreds of billions of stars, and there are billions of galaxies in the observable universe. The distribution of stars within galaxies is not uniform. Stars tend to cluster together in spiral arms, star clusters, and other structures, influenced by the gravitational pull of other stars, gas clouds, and dark matter. The evolution of galaxies is intimately linked to the life cycle of stars. Understanding the relationship between stars and galaxies is crucial for unraveling the complexities of the universe on its largest scales. From the earliest civilizations to the present day, stars have captivated the human imagination. They have served as navigational guides, inspired countless myths and legends, and driven scientific inquiry. As we have learned more about the universe, our fascination with stars has only deepened. The study of stars allows us to trace the history of the universe, understand the processes that create and distribute elements, and explore the fundamental laws of physics. Stars are not just distant objects in the night sky, they are connected to us in profound ways. The elements that make up our bodies, the Earth, and everything around us were forged in the cores of stars. We are, in a very real sense, stardust. The study of stars is a journey of discovery, a quest to understand our place in the universe and to unravel the mysteries of the cosmos.